A high-pressure fuel line running at common rail pressures doesn't just fail from one big shock. Honestly, it fails from thousands of tiny vibration cycles, day after day, until metal fatigue finally wins. On the 4,000 horsepower Caterpillar C175-16, protecting that fuel line and every sensitive sensor around it starts with one absolutely crucial job: getting the vibration out of the base frame before it ever reaches them. Welcome to this explainer, where we're going to dive right into how this giant engine tames those invisible forces.
So, what actually kills a heavy-duty fuel line running at an insane 26,000 psi? A lot of folks assume it's a sudden massive pressure spike from the inside. But the truth? It's much more insidious. They're destroyed from the outside in. We're talking about relentless mechanical vibration leading to metal fatigue. It's a cumulative failure mode, not a single overload event, meaning this kind of damage can quietly accumulate for weeks or even months before it finally snaps. To understand how the C175 prevents this, here is our agenda for today. First, we'll look at isolating engine harmonic vibration. Second, high-pressure fuel containment. And finally, precision speed and timing. Let's jump right into part 1, isolating engine harmonic vibration. The battle against metal fatigue starts literally from the ground up. Right at the physical interface between the massive V16 block and its base frame sits a specialized isolation mount system. This isn't just a hunk of metal, it's a critical component engineered specifically to decouple the engine's primary firing frequencies from the surrounding structure. Without it, the harmonic vibration from 16 cylinders would transmit directly into the frame, silently fracturing fuel lines over time and destroying sensitive nearby electronics like the TCM stepper motor. Now, unlike a rigid mount that basically acts like a highway for vibration straight into the frame, an isolation mount acts more like a heavy-duty sponge. Every single time a cylinder fires, it sends a shock wave through the engine block. Multiply that by 16 cylinders firing in rapid succession, and you generate a constant vibration signature, a firing frequency that just never stops while the engine is running. These isolation mounts are precisely tuned to absorb that specific energy within the mount material itself, stopping it dead in its tracks. Think of it like putting rubber isolation feet under a massive, powerful subwoofer in your living room. If you bolt that subwoofer directly to a hardwood floor, the whole room shakes, right? The windows rattle, pictures fall off the wall. But if you put it on proper isolation feet, the acoustic energy stays completely contained at the source. The C175's engine mounts do exactly the same job for mechanical vibration, protecting delicate auxiliary parts that absolutely were not built to flex. This brings us to a golden rule in diagnostics. The broken component is usually the victim, not the cause. Technicians will often chase vibration-related failures by just swapping out a fractured fuel line or a busted stepper motor without checking the mounts. But if a mount degrades, it lets that raw energy through, and the downstream parts take a beating they were never designed for. Always treat visible mount cracking, oil contamination, or excessive engine movement as an immediate stop and inspect condition. If you don't fix the mount, your shiny new replacement part is just going to fail again. All right, moving on to Section 2, high-pressure fuel containment. Having controlled the mechanical vibration on the outside, we really need to respect the fluid dynamics on the inside. The common rail fuel system on the C175 handles internal fuel pressures up to a staggering 26,000 psi. That is roughly 180,000 kilopascals. To put that kind of force into perspective, a leak at that pressure could literally cut through solid material. It demands an incredibly secure, flawless delivery path. To safely wrangle this highly pressurized fuel into the injectors, Caterpillar engineered a specialized double-wall quill tube assembly. It's a remarkably robust piece of hardware that flows fuel from the inner rail directly past a flow limiter and straight into the cylinder head. It is entirely designed around mitigating absolute worst-case scenarios. So, how does this double-wall architecture actually work? Well, the inner tube is what carries that blistering 26,000 psi fuel. But surrounding it is an outer copper jacket acting as secondary containment. If a metal-to-metal mating surface ever gets compromised, this jacket catches the leaked fuel and safely channels it away from the hot engine parts through a series of internal flutes. It's exactly like the drain pan under your home water heater. That pan is there to catch a slow drip before it floods your entire basement, right? On the engine, this outer jacket routes any internal leak straight to a visible detection port located just under cylinder number 1. You obviously never want to see fluid there, but its whole purpose is to give you an early warning. Catching a few drops early means a scheduled repair. Ignoring it That's a massive fire hazard. Which brings up a great real-world scenario. You're doing your daily walk-around on a C175, and you spot a few drops of amber fluid at that cylinder 1 drain. What is the very first thing you do? Because of the quill tube design, almost everyone immediately assumes it's a fuel leak, but jumping to conclusions right there can send you chasing the wrong repair entirely. You have to follow a strict 3-step troubleshooting rule here. First, actually verify if the fluid is fuel or oil. Oil means you have a totally different issue, like a lubrication seal failure. If it is fuel, step 2 is to inspect the quill tube O-rings. And finally, step 3, you must ensure the connections are torqued exactly to specification. Never, ever guess this torque by feel. Under-torquing breaks the metal-to-metal seal, and over-torquing permanently ruins the sealing surface. And that brings us to our final piece of the puzzle, Section 3, Precision, Speed, and Timing. We're moving from massive fluid pressures down to microelectronics. For this engine to run, the ECM needs to know the exact position of the crankshaft and camshaft every single microsecond. To do this, it relies on variable reluctance. Variable reluctance sensors generate their own electrical pulses just from gear teeth spinning past a magnet. They don't even rely on battery-supplied voltage. It is a completely self-powered system driven purely by the mechanical rotation of the engine itself. The speed sensor sits precisely over the gear group. As the metal gear teeth spin past the sensor, they rapidly disturb its magnetic field, and that generates a highly unique electrical signature. The ECM then takes that constant wave of pulses and translates it into real-time positional data with incredible microsecond accuracy. Now, for total reliability, the engine doesn't just use one of these. It uses a network of them. There's a primary sensor monitoring the rear crankshaft gear, tucked down inside the crankcase toward the left rear. Then you've got 2 secondary sensors up on the top rear of the engine watching the camshaft gear. Working together, they give the ECM a flawless, real-time map to synchronize that fuel delivery perfectly. So, bringing it all together, the mechanical mounts, the high-pressure fluid systems, the microelectronics, they are all completely inseparable. Maintaining those foundational isolation mounts is literally the only thing preventing harmonic vibrations from fracturing fuel lines and blinding the ECM sensors. It all rests on that foundation, which leaves us with one question. If you've been skipping your mounts inspections, what invisible damage might be quietly accumulating in your engine bay right now? It's definitely something to think about before you fire it up next time. Thanks so much for joining this explainer, and we will see you on the next one.